Right. Welcome to the afternoon session, second afternoon session. Our first speaker is Luis Gregorio Dias da Silva from University of São Paulo. He'll tell us about interlayer Coulomb interaction in the bilayer nickelates.
Okay. Can you all hear me? I guess so. Okay. Thank you, Rafael, for the introduction. I'd like to thank the organizers for putting together such a nice workshop and for the invitation to speak to you here. So I'm for those who don't know, the USP campus here in São Paulo. This is a picture of our institute. It's about 30 minutes on the subway, plus a short ride up from metro. Is a very pleasant campus, so invite you all to have been able to visit the campus, to go there and take a walk. It's really nice. So let me first start by acknowledging my collaborators. This is the work of my student Lauro, who's doing his PhD. All the calculations I'm going to show were his. Also like to acknowledge Jorge Martins at the Federal University of Uberlândia, who taught us RPA. And as we heard a lot about iron-based superconductors, both today and yesterday. And I'm going to switch gears a little bit and talk about nickelites, especially this compound here, the bilayer La3Ni2O7, or sometimes called LNO327. And first, I'm going to start off by doing something very risky for a theoretician, which is to do a quick review of the experiments on these compounds. And very risky, especially because we have many talented experimentalists in the audience, but I'll take my chances here. So let me start with this paper, which was from Meng Wan's group in China, where they essentially discovered the high TC superconductivity in these bilayer compounds as under pressure, very high pressure, above, say, 20 gigapascals. And what they find is that you have critical temperatures of the order of 80 K around here. And before that, as you increase the pressure, there is a phase structural phase transition where the angle of these bonds between the oxygens and the nickels goes from, say, about 168 to 180, and it gets a line. And you see that this is usually one of the hidden ingredients for you to get these superconducting state here. So they did that for single crystals. Later, some other groups reproduced these results in polycrystalline samples as well, and here we have a phase diagram which is quite similar. You have a superconducting dome. This is the onset of superconductivity. The blue here is when you reach actual zero resistance, so there's a large difference in temperature between the onset of the superconductivity and the actual zero resistance state. But this was about 2023, 2024, but here again about 10 gigapascals, right? And then just last year, there was another paper from another group where they saw superconductivity at ambient pressure, but in thin films under axial strain. So you have, depending on the substrate where you grow the LNO327, you might get superconductivity or not. If your substrate is SLAO, you do get it at around at the onset about 26 to 40, and the zero resistance state at about 2 Kelvin. So so this is very, very, very nice results that gave a very large boost to the field. And of course, there's another interesting result that came also from Meng Wan's group regarding the nature of the bilayers here. And what they see from inelastic neutron scattering, there is evidence of a very strong exchange coupling between the layers, actually one order of magnitude than the coupling between spins on the plane. So that means that very differently from, say, the cuprates, the layered nature of this material has a very important, seems to be a very important ingredient to understand superconductivity in these cases. So with all these experimental ingredients, of course, there's a lot of theory involved as well. And many people have proposed low energy models to study the bilayer LNO327. So the starting point is to understand what are the bands near the Fermi energy. And this is pretty much well established that at those pressures where you see superconductivity, the relevant bands are essentially these. You have pretty much 4 bands. And a Fermi surface which has a hole pocket here near the endpoint, and also other structures. So you have essentially three pockets, sometimes called alpha, beta, and gamma. The gamma pocket at the endpoint, and this gamma pocket has a strong 3z square minus r square character. So that's the orbital that connects the two planes in the structure. So here's a quick tight binding kind of model that was put together in this paper, which is the one that we use. And this is the largest hopping, actually, right? So it's about half, so these 2 T perpendicular Z, so this is about half a millivolt, so this is 1. And one of the key features in all these theory papers which use these kind of models is that the presence of these gamma pockets seems to be quite relevant for superconductivity. So in the following, we're going to use essentially this tight binding model that reproduces these bands. These are actually calculations by Lotto, who reproduce very well the bands and their character. So what we're going to do is that we're going to include interactions on the models, which encompass both on-site interactions with a local U, and these J's here are going to use, of course, full rotational symmetry, so the U's and J's will be related in some way. But also, we're going to, the novelty here is that we're going to include interlayer Coulomb interactions as well, and see their effect on the properties of the pairing gap of this system. So the important parameters here, since I'm saying it, we're going to use full rotational symmetry. So U prime and U are in a sense related, as well as U perpendicular, and J perpendicular and J are also related to U. So the two main parameters that we're going to be tuning and focusing on are the on-site Hubbard coupling, U, and U perpendicular, right? The Coulomb interaction between orbitals, nickel orbitals in the two layers. And this is going to be a 4-band model. So we have 2 layers and 2 orbitals per nickel site. That's where these are centered, and that's where we're going to focus on the physics and try to understand what happens to, say, the pairing symmetry as a function of these parameters. Okay. In the case where you don't have the Coulomb interaction between the 2 layers, this has been well studied by some other groups, and we're going to focus now on the pairing gap symmetry using the random phase approximation. So the recipe to study the pairing gap symmetry with RPA is to first construct the spin and charge susceptibilities from the non-interacting susceptibility, which comes from the original tight binding model that I showed you with and of course from that you essentially apply the RPA and you get interacting RPA from these matrices. This is sometimes called the matrix RPA, since all these models have a multi-orbital character. And from these possibilities, you can calculate the pair interaction in a singlet channel, which would depend on these quantities. And from this pair interaction core, you can write down your linearized gap equation, right? So here is a version of the Lichberg equation, but at the Fermi energy. So at least we will have information of the gap. The eigenvalue could give us an estimate for what you would get for the TC, but that's not very reliable in this approximation. But at least the symmetry of the gap should be well described in this approximation. So this is, of course, very well known. And essentially, what we're bringing here is the interlayer interaction, which will enter in these matrices here. Okay, so what do we have on the literature before, right, when you study these models as a function, say, of the on-site interaction U, and solving the eigenvalue equation and seeing what the leading eigenvalues are, which will give you the leading pairing symmetry. So most of the works have concluded that the leading symmetry should be S wave, or in the sense S plus minus, where for this particular value of U, which is 1.16, has been shown by some mean field calculations to match the 80K that they see in experiments at 18 gigapascals. So we're going to be focusing on U's around 1, right? And see what's the leading value. So all these papers, they see S wave, but some other, a minority, but still quite a few, have considered different models where they see the possibility of D-wave pairing in these models at precisely these scales. So for instance, this one, they consider a different crystal field splitting could lead or transition from a situation where we have S wave to D wave. So then the question that we're trying to look at is whether the interlayer interactions will also play a role similar to, say, the crystal field splitting, where you can go from an S plus minus to some sort of D wave order. And that's what we set out to do. And here are our results. So we studied everything as a function of the ratio between U perpendicular and U. So when you don't have interlayer interactions between these orbitals, you do get a leading eigenvalue of the type of S plus minus wave, especially in this splitting is very clear for U above 1 electron volt. But as soon as you start increasing, and you don't have to increase the interlayer interactions by much, by about 10% is enough for you to see also splitting in between the solution. We will have a D wave, like in this case dxy, and the S plus minus, but still for large U, S plus minus is the dominant. But notice that this dotted line is moving to your right. So it means that you need more and more on-site interactions for S plus minus to win. And in fact, if you increase the ratio to a certain point for, say, a given value of U, then your leading eigenvalue becomes D wave and not S wave anymore. So you can see, like here, if you fix, for instance, U at that value of 1.16 electron volts and increase the ratio U perpendicular over U at around 20%, the two lines cross. And then the leading symmetry becomes dxy. So in other words, for a fixed value of U, the symmetry will change provided that the interlayer interactions are strong enough. And doesn't mean that it's very strong, it's just 20% will do the trick. So another way to plot these results is to do a diagram of U, the on-site Coulomb interaction, and the ratio U perpendicular over U. And red means that you have S wave, essentially, and blue means that you have D wave. This is essentially the crossover when the two are equal, the two eigenvalues. So if you go, say, if you're sitting here at 1.16, at this triangle, you get S plus minus, and that we have seen this morning. This is a symmetry where the order parameter doesn't have any nodes, but it does change signs when you change the pocket, the so-called S plus minus. And as you increase the U perpendicular, you go to a D wave symmetry where you have nodes along the X and Y axis, right? And not along the diagonal. So that's what our results tell us that what's happening. So this is the main result that about this work. But in the following, I'll try to convince you why that is happening. So we're going to go under the hood of our eigenvalue equations and try to see what are the key ingredients that make this transition as a function of the perpendicular Coulomb interaction, the Coulomb interaction between the layers happen. So the first insight that we get from our results is that the roles of the pockets, especially the gamma pocket, is really important. So first we start with the charge and spin susceptibilities and see what's going on here in both the spin and charge susceptibilities. And of course, we compare that to other results already published, and it fits nicely. And then we start changing the ratio between U perpendicular and U. And the first thing that you notice is that in the charge susceptibility, you start having a small decrease on some of the peaks, especially around the M point. And here, around this peak here between the X, gamma and X, and that's something that is not so big, but it's already to do the trick. Remember, square means triangle means that we are at the S plus minus, or again, sorry, triangle means that we're at S plus minus and square at the dxy. So when you go from square to triangle, you have essentially the changes here in the charge susceptibility. So putting in other way, so if you increase U perpendicular from say 0 to 30% of U, there's a reduction in the charge susceptibility at these three K points, K vectors. And if we go back and look at what these peaks represent, you can see that K2 and K3, they represent some nesting between the pockets, which in the S plus minus wave will connect pockets with the same sign in the pairing gap, while in the D wave case, they connect regions of the pockets with opposite signs. So that's the first ingredient that says that somehow this decrease in the charge energy is related to an increase in the pairing precisely at those vectors. And if you plug that into our eigenvalue equation, this will induce, because of this minus sign here, to a favored pairing gap, resulting pairing gap, where when you go from K to K plus either K1 or K2, you get a minus sign here. So that's one of the important elements here, is that these nesting effects, they will change due to especially the charge sector, due to the increase of the interlayer Coulomb potential, and that will in turn favor a D-wave-like state. So that's the first the first conclusion that we get. The other thing is related to the actual contributions from the pockets for this equation. Notice that here there's a sum on the different pockets. So we could go by hand and see, okay, what's the structure of our the pairing kernel, right? When you are, say, at a given k as a function of k prime. So what happens is that, and then we can compare that when you have 0 Coulomb interlayer interaction and with non-zero Coulomb interlayer interaction, and compare the two. So in this diagram here, blue means that the pairing with the Coulomb interlayer interaction is larger than the one without it, and red is the contrary. Whenever you see blue, means that the scattering at that particular k point is being favored by the Coulomb interaction between the layers. So if you are here, say, at the gamma point, then the scattering at the gamma pocket, say, the scattering at the alpha pocket is favored by the interlayer Coulomb term, while if you are at the beta pocket, if you are at the gamma pocket, the scattering at the beta pocket is suppressed in a sense. So that means that what it shows us, and of course you can do that with different values for k and k prime, and at the end of the day, you're going to see that this perpendicular U term, or the Coulomb interaction between the layers, actually enhances the contribution from the scattering between gamma and alpha pockets in the kernel. Now, the other piece of information is that you can actually go by hand and turn off some contributions. Let me say that, okay, I'm gonna turn off the alpha pocket here, or the gamma pocket here, so this is in gray. Keep only the alpha and beta pockets, and see what is the leading eigenvalue, which symmetry do I get for my pairing gap function. So if I turn off the gamma, I get S plus minus, right? Now, if I turn off alpha and keep gamma and beta, I get dxy. Now, if I can go here and turn off beta, and now I get yet another symmetry. Still this symmetry, but I have nodes in the diagonals. This is the so-called dx square minus y square. So that tells me that, okay, if you are in the S plus minus here, you are with a gamma pocket remove, and if you now remove the alpha pocket, you get to the precise region, the precise symmetry that you would get if you kept all three pockets but increase the Coulomb interaction between the layers. That is consistent with the previous result that I showed you, that somehow the Coulomb interaction between the layers enhances the scattering from alpha to gamma, right? So if you take gamma and get alpha removed, you get the other symmetry even in the absence of the perpendicular Coulomb interaction. So of course you can see if you say, okay, do I really need the gamma pocket to get the proper symmetry? And the answer is yes, because if you just turn off the gamma pocket and increase U perpendicular, you do go to a different symmetry, which is d wave, but you get dx squared minus y squared and not dxy. So you need all three pockets to contributing, particularly the gamma pocket, in order to recover what we're getting. So we can summarize all these, trying to seeing this analysis in this table and see, okay, which pockets, essentially, if you turn on the interlayer Coulomb interaction, which is the resulting symmetry that you get. And the main result is this, that is the one that I showed you. If you have all the pockets contributing, you go from S plus, S minus to D wave. But in most cases, what you would get anyway is that as long as you are considering, say, the gamma pocket, it tends to favor a D wave state as well. So that's and it's very. I mean, the intuition here is that since these gamma pockets come from these orbitals that connect the two layers very strongly, and we know that they are important because the experiment tells us there's a strong exchange coupling between them. That means that what we see is that perhaps this D wave might be prominent even if you have, some 20% of interactions between the two layers. Okay, so this is a summary of this part of my talk. So I have 5 minutes. Essentially, we do have the contributions from all three pockets for a given value of these interlayer Coulomb interaction, about 20% of the on-site one will give you D wave. So that's the main result here. And let me tell you one quick story about this paper that might be useful for students and postdocs. That we submitted this to the archive on February, and then I actually had submitted it to the March meeting, and I presented it at the March meeting, and right at the day that the March meeting started this year, this was published in PRB, which a very similar title, essentially the very similar results, essentially the same system. And when I saw that, I said, how could I have missed this? And in fact, I didn't, because they posted it in the archive 2 days later. So to this day, I'm not sure if I did anything wrong, like did I submit it to the abstract to the March meeting before posting it in the archive, and these guys actually got wind of it? I don't know. But the other way to see it is that this is a very competitive business, so the ideas are floating out there, and people are doing that all the time. So that has happened to me before. Postdocs and students, that might happen to you at some point. In the 3 minutes that I have left, I'd like to tell one more side of the story that Lauro is actually working on. That is something that bugged us a lot. Is that okay? We did all these calculations trying to get the correct symmetry for the system, but for that we needed a linearization, a kind of tight binding model as our starting point. And as we have seen, depending on the tight binding model that you start with, you might get different results. So the way this business works usually is that you start with a band structure from, say, a DFT calculation. You linearize it and produce a 4-band tight binding model. Then, of course, there's some tricks here to produce the models. From that, you get the band structure and the Fermi surface, and from that, you do the RPA, and you get the actual symmetries and susceptibilities and whatnot. So this step here is crucial, right? So one thing that we thought, what is the correct linearization, right? Because you can do different types of linearization or tight binding models, and you get slightly different results that might result in actual different conclusions. For instance, in this paper, they start with a nearest neighbor tight binding model. They do get S plus minus wave, but the shape here is a little bit than the one, say, in this one, where they also get S plus minus wave, where next nearest neighbor tight binding model. And in this case, they went further and got more hoppings, more long-range terms, and they got a different pairing. So this is one of the things that I presented you, that depending on how you do these calculations, you can get different conclusions, so you have to do that with care. So the question we're asking, and actually Lauro had a discussion with our colleagues down the hall who do DFT, and see if we can bypass the venerization effect and construct a local orbital basis straight out of the DFT results. And that's something that we're working on now. And essentially the idea is that you start with your COMSHAM eigenstates from your band structures, and you construct a local orbital, say one of the 4 orbitals in the nickel atom. And of course, you can always do that and project these states. So essentially, you project on a large basis to a small one, like four local bases, and your Fermi surface will now be 3D, but at least you have a description that doesn't pass through any venerization process. Of course, there's the details of the choices of the orbitals that you get, but that's a more controllable approximation. And right now, from that, we get our non-interacting Green's functions straight out of the actual band structure of the DFT. And one thing that we see right off the bat, if we calculate the spectral density here, read at this non-interacting level, you already have some components from bands that are far off from the Fermi energy that would not be included in the venerization. So somehow you have more information than you would get if you only concentrated on these bands up here. So one thing that we get so far and for free is that this gives us pretty much the correct filling for the nickel atoms that is quoted in the literature, which is 2.5, a valence of 5 per 2 nickel atoms, or 2.5 per nickels, where in the venerization you don't. You have to adjust the Fermi level in order to get this right. So, and this only happens because we're considering also the spectral weight from these bands down here. So, I mean, we're cautiously optimistic about this approach. We're now working on converging the actual the RPA susceptibilities, and at some point we'll get some gap functions for you guys, and I'll show properly in the next meeting. So thank you for your attention, and let me show you the view.
All right, we have time for questions. The farthest from me.
Back there if you want. Yeah. Thank you. From a sort of a crystal chemistry perspective, should I be surprised that your UPerp is, I mean, you made the case it's small, but I would have thought a third of the on-site U for 2 atoms which are now sitting with an oxygen in between is actually a really large energy cost to put an extra electron here. So, and I guess it's an effective model, but it almost to me seemed very big. Right.
Okay. Yeah. Okay. That's a good question. So notice that depends on U itself, right? So the fraction can be the actual number can be very small, depending on U itself. So if you're down here around 1%, just a tiny, like 5% value of U perpendicular is already enough to do the trick. So yeah, if you are here on this corner with a large on-site U, then yes, then I would think that the D-wave scenario here is unlikely. But around here, not so much, right? So if you plug it in, I mean, 5% of 1 electron volt, that's not absurd. I mean, that's the point.
More questions? I have a question.
Sure.
Your dxy actually reminds me a lot of the S plus minus in the sense that the gap still had different signs between the
pockets.
the two. So these are bonding and anti-bonding bands, right?
Yes.
So and they have different signs, right? Like if I look at your plot, right? Like the
Like here?
no, the bonding and anti-bonding. The I think you go gamma and beta.
Okay. So okay, all right. So usually when I call bonding and anti-bonding, I would say this which would be
So
gamma.
alpha and beta are not bonding and anti-bonding.
Yeah. No. Well, depends, right? So if you look at the largest hopping parameter, the one that really does the splitting is TZ, right, between the layers, and this one is splits the gamma, and well, let's see here you get the one at X, about beta, right? So this is, I think, bonding and anti-bonding would be whatever crosses here near X, which is beta, and the pocket at the endpoint. So this would be bonding and anti-bonding in the layers, right? So you would,
but if I go back, right, there is both in the S plus minus and in the XY, the sign changes between the alpha and beta bands, right?
Yes.
Because the same remains at the XY there, right?
Yes.
So do you understand why?
So you mean
In the DXY, why there is a
why
pi shift between
see.
the pockets? Yeah.
Oh, yeah, that's a good question. Why this is positive and here is
Exactly.
negative?
Yeah.
That's a very good question. Yeah, I would have to think about it. Yeah, because
It's not that makes this DXY a little bit spicier, right?
Yeah, it's and the fact that but here I think my answer would be that you have to include the gamma as well, right? Because here you have a change in sign between alpha and beta, but also changes in gamma. While here gamma and this section of alpha is with the same sign, and then you change actually this section of beta is the same sign, and this section alpha is different. So you have to look. It's not that all clear because you have this third band, this third pocket.
But since these pockets are touching, how should I think of the gap at the point where they touch, since one is positive and the other is negative?
Okay, the gap is in
the diagonal where that point, yeah.
Yeah, right here.
Yeah.
Well, here it doesn't open a gap, right?
So that, I see. So there would be a node there.
Yeah.
Okay.
Right here. Okay.
All right. Sorry. I just thought this was different. Yeah. More questions?
Okay.
If not, let's thank Luis one more time.
Okay, thank you.
So while Maria prepares,